Greetings and welcome back. In this video, we shall continue with the properties of Fourier transforms. If you recall, we have already solved 5 properties, namely linearity, similarity, the third one being shifting, fourth one modulation property, and the fifth one being conjugate symmetry property. We shall now do the sixth one, which is titled as transform of derivatives. Here we are going to find the Fourier transform of the first order, second order, third order, and so on, the number of derivatives. So how do we do that? Let us first state the property in this manner. If f of x is continuous, that's the first condition, that it has to be a continuous function or piecewise continuous. F dash of x is differentiable, and then the third condition being both f of x and f dash of x are absolutely integrable. That is, their integral values between minus infinity and infinity are finite. So f of x and f dash of x are absolutely integrable. And fourth one would be the main one here. F of x tends to 0 as x tends to plus or minus infinity. So when x is plus infinity or minus infinity, this condition is going to be applied very seriously. So let us not forget, only under this condition can we derive the result. That is, f of x tends to 0 as x tends to plus or minus infinity. Then what the Fourier transform of the first derivative is given by minus is into f of s, where f of s is nothing but the Fourier transform of f of x. So this is the condition. We shall first derive it for the first derivative and then generalize it for nth derivative. So that's how we take this property forward. We shall first start by the definition. We shall rewrite the definition as Fourier transform of f of x to be equal to 1 by root 2 pi integral minus to plus infinity f of x e power isx dx. We need to now find the Fourier transform of f dash of x. So as we normally do, we replace f of x by f dash of x everywhere, and then this becomes Fourier of f dash of x is equal to 1 by root 2 pi integral minus infinity to plus infinity, and the integrand now becomes f dash of x into e to the power isx dx. Now we do have it as udv method, which is integration by parts, and so we shall similarly take it forward in the same manner. Here u is taken to be e power isx and dv is taken to be f dash of x dx. So just as all of us are aware of the integration by parts, so in this case du will be is into e power isx into dx, whereas v will be equal to f of x. As integration by parts formula says, integral u dv is equal to uv minus integral v du. We shall now substitute this in our right hand side and see what we get. 1 by root 2 pi. So let me open the flower bracket first and write the first term, which is u into v, that is e power isx into f of x, that is uv is written, and the limits here vary from minus infinity to plus infinity, minus integral minus infinity to plus infinity v into du. So it is f of x into is into e power isx dx. So from what we have written on the right side, I have written using the formula as mentioned as u dv, integral u dv is uv minus integral v du. This is the formula that I have applied here using the expressions for u, v, du and dv. Now let us look at the first expression. The first expression is f of x. Now if you see, this is f of x and you're substituting infinity and minus infinity, and as per our condition given in the statement is f of x tends to 0 as x tends to plus or minus infinity. So because of this condition, the first term will completely vanish. So this will become 0. The reason here, what is the reason? The reason is since f of x tends to 0 as x tends to plus or minus infinity. Lower limit is minus infinity, upper limit is plus infinity. So finally, what are we getting here? 1 by root 2 pi. That's what we get here. And the next term. So I could pull out here minus is because I'm integrating with respect to x. So I'll take out minus is. What is left within the integral is integral minus infinity to infinity f of x e to the power isx dx. Now this minus is a constant, so I'll take it as minus is into. Now write this within bracket and then recollect what this represents. 1 by root 2 pi integral minus to plus infinity f of x e power isx dx. I am sure you all can guess now what this is. This is nothing but the Fourier transform of f of x. So using that, substituting it on the right side, it is minus is into the Fourier transform of f of x. So what is the left hand side? The Fourier of f dash of x, therefore, is equal to minus is into f of x. Minus is Fourier of f of x is nothing but f of s. Well, when was this finally obtained? Only because we could make the first term here 0. And why was it made 0? Because f of x tends to 0 as x tends to plus or minus infinity. So therefore, this is equal to minus is into f of s provided f of x tends to 0 as x tends to plus or minus infinity. Now this can be generalized. Now we have derived it for the first order derivative. Now generalizing this. Generalizing, you can do it for f double dash, f triple dash. So this becomes Fourier of f double dash of x. What will it become? It will be minus is the whole square. You see, when it is the first derivative, it's to the power 1. If it is the second derivative, it is the power 2 into f of s provided. So you have another condition there. Not only f of x, it is f of x as well as f dash of x. Both should tend to 0 as x tends to plus or minus infinity. So when you're dealing with the second order derivative, you have to have the derivative up to the first which will tend to 0. Continue similarly f of f triple dash of x, the third order derivative. What is the Fourier transform of the third order derivative? It will be minus is the whole cube into f of s provided again here. How many derivatives should be 0? F of x. Start with f of x and go to one order less than what you are finding. You are finding for the third order, so one less will be up to the second order. So f dash of x, f double dash of x should tend to 0 as x tends to plus or minus infinity. I am sure this would have given you an idea as to how we have to proceed further. Generalizing this for the nth order derivative, the Fourier transform of fn of x, the nth order derivative, is minus is whole to the power n into f of s provided. So provided what conditions are true, you have to start with f of x and go to one less than what you are finding. You are finding for n, so f of x, f dash of x, f double dash of x, etc. fn minus 1 of x will tend to 0 as x tends to plus or minus infinity. So pertaining to these conditions, these Fourier transform of derivatives is applicable, and hence that completes the proof. So that's how we derive the Fourier transform of various derivatives of a given function. So we started with the definition and then we used the condition that f of x tends to 0 after applying the integration by parts. F of x tends to 0 as x tends to plus or minus infinity, which gave us the answer ready-made. And then we generalized it up to the nth order. So this is about transforms of derivatives. So we have now learned how to find out the Fourier transform of the derivatives of any order. Now we shall move on to one next property where we calculate transforms of integrals. So we have calculated transform of derivatives. Now we shall prove the property of transforms, Fourier transforms of integrals. Let's look at the statement. It reads that if the Fourier transform of f of x is equal to f of s, then the Fourier transform of the integral. Now look at what form the integral is. Integral a to x. The lower limit is a constant, upper limit is a variable x. F of x dx is equal to f of s divided by minus is. Now we are now calculating the Fourier transform of a single integral of this manner. We shall derive this first and then generalize it for different integrals, different ordered integrals. Let us now start the proof. Now let us first, this does not start with the definition, but let us assume now that the integral that you are taking is the function of x, let us call that integral a to x f of x dx, which we have chosen in our statement to be a function of x. It has to be a function as one of the limits is a function of x. So let it be called g of x. So when we differentiate both sides with respect to x, I am sure you will agree that f of x will be equal to g dash of x. Since the integral and differentiation are reverse operations, when you differentiate both sides with respect to x, you will get f of x equal to g dash of x. Let's call them as 1 and 2. By property number 6, we proved in the previous property. By property 6, what did we prove there? The Fourier transform of the first derivative. Now let me take that first derivative to be g dash of x. What is it defined as? Minus is into the Fourier transform of g of x. This is what we derived in the previous property. So we shall now apply property number 6 to g of x. So instead of g of x, the derivative is taken as g dash of x. So it becomes minus is into the Fourier of g of x. Now, g of x that we have here is nothing but, keep it as it is, substitute for g dash of x in this. So what is g dash of x from 2? It is f of x, and right side that you have is minus is into the Fourier transform of what is g of x? It is integral a to x f of x dx. That's all. We have now proved the result. We are using 1 and 2 in the property 6. 1 and 2, property 6, which is applied for g of x. And then we substitute what is g dash of x and g of x and rearrange the terms. Finally, keeping Fourier on one side of integral a to x f of x dx, we can now write it as Fourier of f of x divided by minus ix. Minus is, and this is nothing but, what is Fourier of f of x? Fourier of f of x is f of s. So therefore, we have proved the theorem that integral a to x f of x dx is nothing but f of s divided by minus is. So very simple proof that we have here, and hence we have proved the respective result. So in this particular video, we have learned two important properties on transform of derivatives, and these are the transform of derivatives, and the next property is the transform of integrals. Now we use them in problems, so it's important not only to know how to derive it but also how to apply it in problems, which we shall see in our subsequent videos. So with this we wind up this video. In the next video we shall see some more properties. Thank you. See you soon in my next video.